In this video, we're going to be working a Unit 3 FRQ. So, show all your work for each part of the question. The parts within the question may not have equal weight. A curved track leads into a circular loop of radius r, as shown in the figure 1. A block of mass m is released from height h on the track. The block slides down the track and around the loop without losing contact with the track. All frictional forces are negligible. Okay, so the block, it starts up here. So initially it's at the top, and then it slides all the way to the bottom, and it goes around this loop. So it goes around this loop, and then we know that it never leaves the surface of the track, and the friction is negligible. So if we know that the friction is negligible, we know that we'll later be able to use conservation of mechanical energy. But for right now, let's draw the free body diagram for this block. So the block at the top of the loop. When it's at the top of the loop, it's like this. And we can see that the Fn, the normal force is always going to be, so if you have your object here, and your normal force is always going to be acting perpendicular to the surface. So it's always going to be perpendicular to the surface, Fn. So here, the normal force is going to be pointing this way, but also you also have the weight of it. So I'll just put this here, Fn, and you also have the weight, which is equal to mg. So if we draw this, it's just going to be, we're going to have the weight, which is equal to mg, and we also have the Fn, which is pointing down. And this is because it's upside down, because normally it would be up. But in this case, the surface is just flipped upside down, but it's still acting, there's still a normal force because it's not going through the ramp, it's staying on the surface of the ramp. Now the dot in figure 2 represents the block. Okay, we did that. So, starting with conservation of energy, derive an expression for the speed of the block at point P. Okay, so as I said earlier, we have conservation of mechanical energy, and that's because there are no external forces, and there's no friction. That's why. So because there is none of this, we know that we have E initial is going to be equal to E final. So we know at the initial point, so at release, the initial point, we know that the kinetic energy is going to be equal to 0. And we also know that the initial potential energy is going to equal to mgh. Let's actually mark this on our track. So up here, we know that our energy is going to be all potential. And then we know that once it's finally down here, that it's going to be all kinetic. And we know at the top of the loop, at the initial, and then we also know that here at the initial point, the kinetic energy is equal to 0. That's equal to U initial. That's equal to mgh. Here at now let's talk about point P. So at point P, we know kf is going to equal to 1/2 mv squared. Uf is equal to mg/r. Now, let's just describe this. Just look at these 2 points. So now that we have those, let's rewrite those down here. So at release, and then at point P, top of loop, that's going to be kf is equal to 1/2 mv squared. Uf is equal to mg/r. Now, conservation of energy is initial is equal to final. So we can write out our general equation for that. So it's like kinetic energy plus potential energy is equal to kinetic energy plus potential energy. Initial, final, initial. We know at the beginning that this is equal to 0. So we can cross out that. And then here we know that we have km and uf, so that we can write this. So we're going to be left with mgh for potential energy is equal to 1 half mv squared plus mg times 2r. Now we can see we can cancel m because there's an m in each of the terms. Now we're left with gh is equal to 1 half of v squared plus 2gr. Now we can rearrange, which means that we can subtract 2gr. After we subtract, then we just have that gh is gonna be equal to gh minus 2gr is equal to 1 half of v squared. Now after this we can multiply both sides by 2 because we want to cancel out that fraction. So if we do that, then we can just do this. So now we have to multiply this by each of the terms. We're gonna have 2gh minus 4gr is equal to just v squared. Now if you can see here, we have a common term, which is just 2g that we can factor out. So we can factor out 2g, and then we're going to be left on the inside with h minus 2r. So that's going to be our v squared, and now we just want to get v. So v is just going to be equal to 2g h minus 2r. And that is our result. Now, that's our speed. Derive an expression for the force exerted by the track on the block as the block passes through point P as a function of the initial height of the block. Express your answer in terms of m, r, h, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference booklet. So, as we know, at the top of the loop, we know that from our FBD, we know that mg, and we also know that Fn, they both point down for the block, and that's towards the center. So if we look here, we can see that they're pointing towards the center. This is the center. So you can also imagine that you have a force here, which is your centripetal force, which is like Fr. And we know the centripetal force. What does the centripetal force do? It keeps it moving in the circle. It perpetuates the circular movement. It's circular motion. Circular motion. So that means that we can use the centripetal condition. So the centripetal condition is that the summation of the centripetal forces is going to be equal to m VFR is equal to divided by r. That's going to be equal to mg plus n is equal to mv squared over r. That's n, that's the weight force. That's weight plus n is equal to mv squared over r. So you know that those both, if you add those both, those are going to, because both these forces, they both contribute to the centripetal force. It's also like, yes. So now after this, what can we do? We can substitute in our earlier value. So we see v squared here, right? We already solved for v squared down here. V squared over here was just this expression. Let's just bring this up here so we have this for reference. You can always use your answers from past results if you think you're kind of lost, because there's a lot of just substitution in the physics. It's reusing what you already have. So you have n is equal to m times 2g times h minus 2r divided by r minus mg. Now, what can we do? We can factor out mg, because we see that. We can factor that out. That's going to be mg, and then n is equal to this. This is going to be 2 times h minus 2r divided by r minus 1. Now, you can simplify the inside of the parentheses. This is going to be 2h minus 2r divided by r minus 1 is equal to 2h minus 4r divided by r minus 1. Now after this is equal to 2h minus 4r minus r over r, because you can just rewrite 1, that's just the same thing as r over r. Now after this, you can rewrite this as 2h minus 5r over r. So now, if you rewrite the whole entire thing, that's n is equal to mg 2h minus 5r divided by r. And we can also check this. If you want to check this, we can use the minimum height for contact. If we use this, we know that the block just maintains contact when normal is equal to 0. So that means you can set mg 2h minus 5r divided by r equal to 0. If so, you have 2h minus 5r is equal to 0, and then h is going to equal to 5r over 2. And that's right. If the frictional forces between the block and the track were not negligible, indicate which of the following would be made to the track to allow the block to still pass through point P without losing contact with the track. So, let's see here. Lower the initial height h. If we lower the initial height h, this is just going to decrease our total energy, which is not right. That's not what we want to happen. If we lower the point P, this is gonna reduce required potential energy at the top. So that means that it's going to have a less amount of potential energy when it's up at the top, which means, like, you know, as you keep going on the track, you just pick up more and more of that potential energy is being converted into kinetic. So are we still, like, if you lower the point, then it's like making you rely less on all that potential energy, and you're saying, like, okay, it's okay if I have more of this kinetic energy. Now, this was probably our answer, but let's look at the last one just to verify. So move the loop further right. So what this does, that's just going to increase your distance traveled. And if you increase your distance traveled, that means that there is more energy loss. And that means that you have, and remember, you have friction. So that means that your total energy is going to be converted into a form that you cannot use. So that's going to be less potential and less kinetic, which is not what you want. Therefore, it is just the second option.